phase changes of water. In the upper left of the screen, you see two water molecules. The covalent bonds between the oxygen atom and the hydrogen atoms in the water molecule are very strong, making water a stable compound. Notice the polarity of the water molecule. There is a positive and a negative side. Water molecules are attracted to each other because the positive, oxygen side of one water molecule is attracted to the negative, hydrogen side of another water molecule. In order for water to change states from solid to liquid and from liquid to gas, these hydrogen bonds between water molecules must be broken, and this requires energy. In this animation, we will follow 1 gram of water as it changes from solid to liquid, from liquid to gas, and from gas to solid. The chart in the upper right shows the temperature changes and total energy required in calories as 1 gram of water changes from ice to liquid water and finally to water vapor. You may pause the animation at any time to study the chart and to examine the molecular view box in the lower right. As soon as the ice warms to a temperature of 0 degrees Celsius, it begins to melt. It requires about 80 calories of heat energy to melt 1 gram of ice. Notice that as energy is being added to melt the ice, the temperature does not increase. As you see in the molecular view, in order for the ice to melt, the water molecules must gain enough kinetic energy to move more vigorously and break some of the hydrogen bonds. The energy used to melt ice is, in effect, stored in the liquid water as latent heat. Next, in order to raise the temperature of the liquid water to its boiling temperature of 100 degrees Celsius, more heat must be added. To completely vaporize 1 gram of liquid water at a temperature of 100 degrees Celsius, an additional 540 calories of heat energy are required. This is known as the latent heat of vaporization. In the molecular view box, you can see that the molecules of water vapor are now highly agitated. As the animation continues, we see another phase change, the direct freezing of water vapor into ice. This process is called deposition, or simply sublimation. If the water vapor is at a temperature of 100 degrees Celsius, about 720 calories of latent heat must be released in order for this process to occur. Notice in the molecular view that as latent heat is released and ice forms, the water molecules lose some of their kinetic energy so that the hydrogen bonds can again form between the water molecules. Next, we see the 1 gram of ice heated and converted directly into water vapor through the process of sublimation. As you see in the molecular view, in order for the water molecules in the ice to gain enough kinetic energy to convert to a vapor, the latent heat of sublimation must be absorbed. As the animation continues, the water vapor changes to liquid water in the process of condensation. If the water vapor is at a temperature of 100 degrees Celsius, about 540 calories of latent heat must be released in order for condensation to occur. Once the 1 gram of liquid water has cooled to 0 degrees Celsius, 80 calories of heat energy must be released as latent heat of fusion in order for ice to form. The sequence of phase changes illustrated in this animation shows idealized circumstances, such as the vaporization of water at its boiling temperature. In nature, evaporation of water can take place when the temperature is far below the boiling point. In fact, the majority of water vapor in the atmosphere is added through evaporation rather than through the vaporization of water at 100 degrees Celsius. In reality, the latent heat of evaporation is slightly different from the total values you see in the animation chart. Understanding the nature of the exchange of latent heat during phase changes is essential to understanding many atmospheric processes. For example, evaporation is a cooling process because latent heat is absorbed, while condensation is a warming process because latent heat is released.